This is question number 23 from the 3.4 MyLab Math homework. And in this question, we're told that the number X of bicycle helmets a retail chain is willing to sell per week at a price of P dollars is given by this equation. So this is a price demand equation. And this equation is defined for prices between $20 and $100. So this isn't written in function notation, it's written as an equation, but X is going to represent the demand. X represents the number of bicycle helmets being demanded, and P is representing the price at that demand level X. Okay, so demand and price are connected. If you know the demand, you can figure out the price at that demand level. If you know the demand level, you can figure out the related price and go back and forth. Okay, so what are we asked to do? Well, first of all, I see that we're given this graph. I think that's just extra info, but it is emphasizing here that our input, which is on the x-axis, is price in dollars, and our output, which is on the y-axis, is our demand. Okay, so that's interesting. So price, P is our input, and X is our output. So this graph does kind of help me read my inputs and outputs. That's very important. Anytime you're working with a function, think about what's your input, what's your output, and what are those things representing. So the graph can kind of help me do that. We're only given this equation here where x equals 78, square root of p plus 25 minus 300, and that's this graph. There's another graph on there. Maybe we'll need that later, I don't know. But we're looking at this graph right here. Okay, now what are we asked to do? Okay, what does A say? A is just asking us to find the derivative. Straight up find the derivative. And when I read this notation, remember a derivative is just a slope. It's a rise over run. So that's going to be your change in outputs, which in this case, our output is X. That's the number of helmets. Number of helmets. Okay, demanded. And so rise over run, change in output over change in input. And in this case, our input on the x-axis there is our P, which is our dollar amount for that demand level. And I should put a little arrow there so it doesn't look like an ordered pair. Okay, so I'm just kind of getting in my mind what these units are telling me. So change in helmets, the demand level, how is the demand level changing with respect to the price? Okay, so we're going to find this derivative. Another way to write this, okay, if you were going to write this in function notation, it would look like this, that X is a function in terms of price. So it's saying if I input the price and I follow this calculation, it's going to calculate the demand. So if you want to write in function notation, you can. So another way to think about this is if you're taking the derivative of this, if you want to know the change in demand over the change in price, that's just X prime is basically what we're finding here, is X prime. X prime is the change in demand with respect to the price. Okay, so there's lots of ways to read this. You can also write this notation. Instead of using F of X notation, you could use X of P. You know, that's still function notation where we're showing that price is the input, and then if I follow whatever the rule is, I'm going to calculate demand. So there's lots of ways to write this. Getting used to the notation is the hardest part in calculus, in my opinion. But let's go ahead and find that derivative. Okay, so I'm going to come over here where I have some more room for part A. So my equation was x equals 78 square root of p plus 25 minus 300. And again, if I wrote that in function notation, I could see that my input going into the function is a p. That input is going here, which is part of this binomial. And we're going to end up using our power rule, but we have to rewrite it with a fractional exponent. We can't have a root in there to use our power rule, so I'm going to go ahead and rewrite that square root as a fractional exponent 1/2. And again, I can see my input is going in to a linear base here. So I'm going to use my power rule with my chain rule because that base is not just a plain variable. It's in this case, it's a binomial, a linear binomial. So let's go ahead and find our derivative. We can do that. We're just going to do power rule with chain rules. Let me write that out. We are doing the power rule with the chain rule. Okay, we have to do the chain rule this time. Okay, so here we go. So I'm going to take the derivative of this. Oh, instead of doing x prime, they're saying the change in x, change in the output, with respect to the change in the input. They're using this notation there. Okay, so let's go ahead and do this derivative rule. Okay, the power rule says you drop that exponent down to the front and multiply it. So I'm going to end up doing 1/2 times 78. Then I rewrite my base exactly as it's given to me. Then I decrease that exponent by 1. Then I need to tack on the derivative of the base. Okay, and then over here I have a constant. I'm subtracting 300, that's a constant. So the derivative of a constant is just going to be 0. So I don't have to write that. It confused me later, so I'm not even going to write that in there. But let's go ahead and finish this derivative. Okay, so what do we get here? I get the change in x with respect to p. I'm going to do 1/2 times 78, that's 39. I rewrite my base exactly like I see it. When I decrease my fractional exponent by 1, that brings me to negative 1/2. And then when I take the derivative of the base there, again, I'm just going to be doing my power rule. It's going to be doing my power rule there. So that derivative is what? Just the derivative of p, a plain old variable. The derivative of plain old variable is just 1. But if you need to do your power rule, it has an understood exponent of 1. When I drop the exponent down to the front, I end up doing 1 times 1. I rewrite my base. I decrease that exponent by 1, but that's an exponent of 0. And then technically, we tack on the derivative of the base, which is just a 1, because it's a plain old variable. So I end up getting 1 times 1 times 1. It's just going to be 1 there. And you can also just see that using some algebra, right? So this is a linear function. We're used to seeing it being written as like y equals mx plus b, but instead of an x, they're using a p here. But still, it's that mx plus b, where m is a 1 slope, a slope of 1, and my b would be the plus 25. So derivatives are just slopes. The slope of a linear, right there in front of the constant, is a 1. However you can see that, the derivative of that is 1. Okay, so when I go to multiply all that together, my derivative comes out to be 39p plus 25, that's my base, my binomial base, to the negative 1/2 power. And you can stop here. You do not have to rewrite this derivative. You can just type it in. If you use the help tools on MyMathLab, what they're going to do is they're going to rewrite that fractional exponent, that negative exponent, first of all, as positive. So they're going to relocate the base to have a positive exponent, and then they'll go ahead and translate that fractional exponent back into a root. But there's no mathematical reason to do that. So you can just stop right here and type that into MyMathLab. So let's go do that, because I don't know what part B is yet. So I'm going to go type that in. Okay, here we go. Here it is. Okay. Oops. Maybe not. There. There it goes. Okay, let's type that in. So it was 39 parentheses P minus... Okay, 25, close my parentheses, and then I need an exponent going on here. Might have to plug my keyboard back in. Okay, exponent, oh no, I got it. Okay, exponent to the negative 1/2. Okay, negative 1/2. Okay, let's see if it'll recognize that fraction. No, I need to change my fraction bar. Did I do the wrong one? Do I have to type it in as a fraction? Okay. You know, I can type 0.5 because that's 1/2. That's easier to type than a fraction. What? What is... Oh, it's plus 25. Oh my gosh, guys. It's plus 25. So let's type that in there. Okay, let me just plug my keyboard back in. Backwards. There it goes. Okay, plus 25. Ooh, that was my final check. I was getting nervous there. Okay, so now it's asking us some follow-up questions about interpreting this. So now we're supposed to find the supply and the instantaneous rate of change of supply with respect to price when price is 75. Okay, so all we need to do there is we're going to plug $75 into the original equation, because that original equation told me the demand for a price at P dollars, right? So if I just plug 75 into there, that'll tell me my demand level. And then I'm going to plug 75 into my derivative, and that'll tell me the instantaneous rate of change of that demand. So we'll go ahead and do those two calculations real quick. Okay, so I went ahead and wrote that original equation, but I replaced the P with $75, and then I rewrote my derivative rule, but I replaced that P with a price of $75, and I just threw those in my calculator, and I got these two outputs. Okay, so those are my outputs. Now we have to interpret them. So remember, in your original function, it was just telling you the demand at a certain price, right? So that you have to think of your units here. So when I plug price into my equation, it's calculating the demand, which was number of helmets. So I'm actually going to come over here and say that's 480 helmets demanded at a price of $75 per helmet. And then this 3.9, that's the instantaneous rate of change at that point in time. Okay, so, and I can kind of come over here just to connect it to this graph since they gave it to us. $75 would be, you know, in here somewhere, like, I don't know, in here. $75 would be somewhere in there. Okay, and if I backtrack up to my yellow highlighted graph there, I don't know, about right there, I can see that the tangent line, okay, we can see, yeah, that demand level of 480, you know, if I backtrack here, it seems reasonable. I mean, it's close to 500. So the number I got from my demand is making sense with the graph. I can see it's a positive slope on that tangent line. So a derivative of positive 3.9 makes sense. Okay, and then what is that 3.9 telling me? We have to think of our units on our rates of change. So change in output over change in input. So what were the units for the output? The output was the number of helmets. Okay. And then we have change in outputs over change in input. So the input was the price in dollars. So when I interpret this instantaneous rate of change, I'm going to say that demand is increasing by 3.9 helmets per each dollar increase in price. So let's go put all of that into my math lab to see what that looks like. Okay, so when the price was $75, the supply was 480. I guess we don't put units there. I don't know, it should be 480 helmets, but I think we just put 480. If that's it, it's going to make me angry. Let's see, I'm checking my answer. Units, my math lab. Okay, well, so let's see this one. When the price is $75, the instantaneous rate of change of supply with respect to price is, I guess I just typed 3.9 and don't put the units? No! Minus 1,000,000 points if you do this on a quiz or a test. Oh, I see. Now they're going to have us put it in a sentence with the units. I still don't like it, but let's go ahead and do that. So at a price of $75, the supply is 480 bicycle helmets per week. And the supply is increasing, since my derivative was positive, at a rate of 3.9 bicycle helmets per dollar. So let's check that out. Well done. Okay, thank you, my math lab. Okay, if you have any follow-up questions on this problem, don't hesitate to ask. I am happy to help. You can reach out to me via email during my office hours, or you can contact our amazing instructional associate, Madhavi Pratapa, or any of our tutors at the Learning Lab.